We're going to start talking about different properties. We have all the foundational stuff that we've discussed previously. We have a bunch of different properties we're going to talk about. And the way that I want to do this is I'm going to go through these videos somewhat quickly. It doesn't mean the videos are necessarily going to be short, but I'm not going to go into a lot of depth with each of these properties. I want you guys to watch these videos to be able to see some of the things that we're going to talk about. And then in class, we can talk about it more. We can read up on it. We can work problems on it. But I want you guys to have the familiarity behind it before we start discussing it in class and together. So we're going to talk about thermal properties first. First, we're going to talk about what heat is. Heat is our thermal energy. It's transferred between systems with different temperatures. So if I have two different things that are in contact, or heat is flowing between two things, that is when we have two systems with different temperatures. Temperature is a measure of the average kinetic energy of the particles in a system. So real quick, I want to talk about the Maxwell-Boltzmann distribution. And what this is it shows the kinetic energy and the number of particles that I have in my system. So let's say that I have a system, and the system has, let's say, 1,000 particles in it. What I can do is, theoretically, what we could do is we could measure how much kinetic energy each particle has. And so somewhere here, wherever our peak happens to be, that right there, that's going to be our most probable kinetic energy. If I just say, what's the most probable kinetic energy that we're going to have in this system, it's at our peak. And let's say this material is at 50 degrees Celsius. And so what I could do is I could figure out what the most probable kinetic energy is. That doesn't necessarily mean that it's average. The average might be a little bit off center, and the reason for that is because these are not symmetrical. So if I have something, let's just say, to make it easy, let's just say that I have a glass of water, and the glass of water is at 50 degrees Celsius. We know that it's not at boiling point, but if you've ever had a glass of water left out on a counter, or if you've seen some water spill and a little while later the puddle is smaller, or maybe that puddle's gone, we do know that evaporation happens, and it doesn't necessarily have to get to 100 degrees Celsius. If I increase the average kinetic energy of all these particles, I'm going to get a new probable kinetic energy, and I'm going to have a new average kinetic energy. And what we have here is it shows that we have, in both cases, some particles that have a very, very high kinetic energy. Let's say that for water to evaporate, we need to get to about this point right here. We can see that even at 50 degrees Celsius, there are some particles in our system that have that much kinetic energy. Not a lot of them, but some of them do. At 100 degrees Celsius, there's much more of our particles which have the thermal energy to be able to evaporate. And so just a quick overview of what heat is, what temperature is, and how it can work, and really getting down to the microstructure, the fact that temperature is not a microstructural thing, it is a macrostructure. It's a big picture type thing, but really we want to be looking at what's happening on this small scale. So, what does heat actually do to a material? Number one, it causes phase changes, and we've done that in chemistry a little bit with our phase diagrams. We have solids, liquids, gases. We also have some change in solid phases or structure. We can go from an alpha phase to a beta phase, and our heat will allow us to do that. The other thing that happens is that within a phase, there can also be a temperature change. And what's going to happen if even within a phase, if I don't have any type of phase change, what is that change of temperature going to do? What is that difference in heat, in that thermal energy going to do? One of those things is going to be thermal expansion. I have this picture here. This picture is our energy versus distance graph. This is the same thing that we did the very, very beginning of the quarter when we were talking about ionic bonds, and we have some attractive force and we have a repulsive force, and we balance those things out, and this is our net energy that we can plot with that. Remember, we had this minimum here, and we called that minimum E naught. It was at our minimum energy, and we were at position R naught. All right, and that was fine when we were just talking about minimum energy, and we wanted to just know kind of what that baseline radius was going to be. And I have this picture off to the side where I'm going to put an L here for L naught. I have this picture off to the side. Let's say I have 5 particles, 5 atoms, and at this low energy, it has this length. What happens when I actually increase the energy? So let's say that I am at energy E1, and that's going to be right about here. The question is, what's my radius? Is my radius going to be smaller than my R naught, or is the radius going to be larger than my R naught? And if you've thought about this before, or you've talked about what happens when we heat a material, you'll probably say, well, it's going to get bigger, so it's going to be this one on the right-hand side, because radius, the length gets bigger, and so if the length gets bigger, that means the radius, the bond length, is going to get bigger. But how can we know that for certain? How come it's not going to be this minimum side? How come it's not going to get closer together? And the real answer to this is, well, it's not going to be the minimum, but it's also not going to be this maximum all the way to the right-hand side either. What's going to happen is we're going to have some type of equilibrium that we're going to have to find. When we add energy to a system, these atoms are going to start vibrating. They're going to start stretching and compressing. And so there will be a point where it's going to compress actually smaller than R naught. And there's going to be a point where it's going to stretch larger than R naught. And so we're going to end up with an average. The average is going to be in between those two things. So somewhere in between there, we're going to have our average bond length that we're going to call R1. And so the look of what's happening on the average is, on average, they're stretching apart. And so this is going to be my length 1. And length 1 is nothing more than our L naught here plus a little bit more length. We do this one more time. I can say, what about at energy 2? Well, at energy 2, it can contract a little bit more, but it can expand quite a bit more. And so I'm going to have this spot in the middle that I can call R2. And again, if I look at these atoms, they're going to be stretched out even further. I have L2, my length. And what we end up having here is we have this picture where my average bond length, the radius, is going to increase. It doesn't mean that the bonds are always increasing. It doesn't mean they're always decreasing. But what it means is that the average is increasing. And that's why we tend to see thermal expansion with a lot of materials. And so I have a little bit of mathematics here. We have our linear thermal expansion, where we have the length, our final length, minus our original length. So if we were going to look at that here, we have, and I didn't scroll down far enough, so I do kind of have a little sloppy. There we go. All right, so I have my final length. Let's say my final length is L1, and it was originally at L0. If I subtract the two, I get my change in length. I divide that by my original length, and that's going to equal some coefficient. I call this my linear coefficient of thermal expansion. This is alpha subscript L because it's my linear coefficient. And I multiply that by my change in temperature. What's my temperature difference from my length 1 to my length 2? And we can simplify that a little bit. And so I simplified that first equation. This is the exact same equation. It's just a little bit in a little bit more simple terms. Our change in length divided by our original length. So we have this normalized change in length. And that's going to equal our linear coefficient of thermal expansion times whatever change in temperature happened between those two lengths. We can do that again for volume. And it's as easy as just substituting all of our L's for V's. I have my change in volume divided by my original volume. That's going to equal my volume coefficient of thermal expansion, not times my volume, times my change in temperature. It's a pretty simple equation. You just got to know what your beginning and ending states are. What we want to do is we want to know kind of what is this relationship between our linear and our volume coefficients. For an isotropic material, 3 times my linear coefficient of thermal expansion is going to equal my volume coefficient of thermal expansion. And that's because in each dimension, it's going to have some effect of what's happening as we expand. So it's going to expand in our x direction, our y direction, and our z direction. So if I take our linear thermal coefficient of thermal expansion, multiply that by 3, I get my volume coefficient of thermal expansion. Question is, why wouldn't this be true for an anisotropic material? An anisotropic material is a material where the properties are not the same in different directions. And so in different directions, maybe the material acts a little bit differently. And if it acts differently in one property, it will act differently in other properties. In one direction, it might act one way. It might expand or contract one way. In a different direction, it's going to act or expand differently. And in the third direction, it'll also expand differently. And so it's not as simple in an anisotropic system to just sum them all together. So what would the equation and coefficient for area thermal expansion be? These are things that I want you to think about. We can talk about these in class. If we wanted something between here, if we didn't want our linear and we didn't want volume, if I wanted an area thermal expansion, what would the equation look like? And not only what would the equation look like, I don't want this to be volume again. What would the area coefficient be? What would the area coefficient of such an equation be? If a material is anisotropic, what would the area? Oh, sorry, that was correct. I was looking at the wrong one. All right, so we'll go back up to this one. I'll say that one more time. So what would the equation and coefficient for the area thermal expansion be? And then secondly, if a material is anisotropic, what would the area or volume coefficient be? So it wouldn't just be as simple as multiplying the, in the case of volume, multiplying the linear coefficient by 3. What would it be then? And why would it be that? Another question would be, is there any other mechanism that would cause a material to expand due to heat? And there is one, so I'll give you that one. And I want you to think defects. So in between you watching this and us talking in class, try to figure out what one of those things might be that would cause some type of expansion. I will give you a little bit of a hint here. And the hint is, do all materials expand when heated and contract when cooled? And the answer is no. There's an odd property. It has to deal with entropy. It's where entropy is going to be the driving force of what's happening. And so what we do is we have something called an entropic spring. An entropic spring is a spring that acts due to entropy more than it acts due to energy. For an elastomer, heat causes contraction and cooling causes expansion. And an example of this would be a rubber band. In its natural state, rubber molecules are highly entangled. As temperature decreases, there is less thermal energy. And this means there's less possible states. I do have a little bit of thermo here. If you want to take a look at it, go ahead and do that. We're not really going to get into it right now. If you really want to talk about it in class, we can. But the idea here is, since stretching is non-spontaneous and temperature can't be negative, this means that my term T, change in S, that's negative. And so when we stretch it, heat's given off, so our delta G is negative when our tension is removed. Basically, all I'd like you to get out of this, though, for now, this isn't necessarily a thermodynamics class, is if I have only a few ways to order something, and sometimes I do this with paper clips. So I'll chain a bunch of paper clips together, and we'll kind of stretch them out, something like this. If they're nice and long, there's only a few ways to order them. And if there's a few ways to order them, that tells us something about our entropy. If I want to be able to order it a few more ways, I can compress them a little bit, maybe have them bend back on each other a little bit here and there. And as I do that, there's more ways to order it, and I'm doing that by shrinking it. And if I just pile all of my paper clips on top of each other, something like this happens. There's a lot of ways for this to happen. So this is something to do with entropy. And if you're unsure what entropy is, if you haven't gotten to that point yet, we will talk about that in class as well. I do want to show you a quick video that I have of this. This isn't a great video. I made this a couple years ago, maybe last year, I guess it was. And I made this just kind of for me. I was testing some things out that I was going to do in class. What I did was I set up this water bottle hanging from a rubber band. So you can see the rubber band there. It's hanging off the end of this cart. And I taped a ruler off to the side of the cart as well. And I am working on getting the camera set in one spot. What I did was I got a hairdryer, nothing fancy, just a hairdryer, a little bit of heat, and you'll see the bottle start to kind of bounce around a little bit. That's because the air is kind of moving it around, but the hairdryer is also heating up the rubber band. And what we see here, it only takes a few seconds for this to happen. We can actually see that the bottle is raising up a little bit. And so what I do is I turn the hairdryer off. That only took a couple seconds, and I turn the hairdryer off, and it only takes a couple more seconds for it to stretch back out. And so then I turn it back on, and it lifts back up. And then I'll turn it back off, and it will extend again. So in this case, it's an entropic spring. It's a rubber band, but heat is actually causing it to contract. And it's contracting enough to where it can actually lift up this bottle of water. And so think about that one. We can have a good discussion about that one. And again, that might have something to do with this question here. Is there any other mechanism that would cause a material to expand due to heat? And I'll give you maybe one other word here. Other than this picture up here, which is our change in energy. So is there anything else that might cause it to expand other than our change in energy? Something else that we can talk about is heat capacity. Heat capacity is the heat needed to raise a system by 1 degree. So I have this system. It doesn't matter how big the system is, but I can say that my change in heat, which is Q, is going to be something, and then I'm going to have some change in temperature. How much heat does it take to change it by 1 degree? If I have this capital C here, I'm using heat capacity. My units would be whatever heat units I want to do over whatever degree units I want to do. This again isn't heat capacity. I did a little copy and paste earlier today, so I got to fix this. Specific heat. Heat capacity and specific heat are similar. Specific heat is the heat needed to raise a system per unit mass by 1 degree. We use a lowercase c for this, and it's very, very similar equation, other than the fact that I have mass in here, and mass is on the bottom. The idea is we actually care about the size of our system at this point. So it would be very different if I had a tablespoon of water, and I say how much heat does it take to heat 1 tablespoon of water 1 degree. I'd get one very specific value, as opposed to saying how much heat would it take to raise an ocean of water by 1 degree. That heat would be significantly different. With specific heat, what we do is we normalize it by taking into account our mass. I say, you know what, I want to know just what water does in general. I'm going to take mass out of it by dividing out the mass. And now I know what water does, how much heat water takes to be raised by 1 degree. And it doesn't matter whether I have a lot or a little. That's what specific heat does. Heat capacity is just for a system, any size. One side note, in thermodynamics, there are constant pressure and constant volume heat capacities. For materials, for solid materials, I should say, there's very little difference between the two because solids are mostly incompressible. So there's really no need for us to distinguish between the two right now. If you want to get very specific, we can do that, especially at higher temperatures. We might care a little bit more about it. But for now, we're just going to say that our heat capacity is, we don't have to have the two, our constant pressure and our constant volume. How does heat move through a material? Well, it goes from hot to cold. We've probably known that for a long, long time, maybe talking about that even as far back as elementary or middle school, probably definitely high school. You probably started talking about that in your physical sciences. And so we know that's the idea, but the question here is, okay, well, what's the mechanism for that heat transfer? Why does it actually do that? Materials are made from atoms and molecules that are bonded together. Heat must be absorbed by one particle, and this particle is either the atom or the molecule, and then it can be given to another. So first it has to gain a little bit of energy, and then it can pass it along to something else. Each particle, each type of particle, every molecule, every type of atom, it has different thermal properties, such as things like specific heat. Materials have different microstructures, and so maybe one is crystalline, maybe one is body-centered cubic, one is hexagonally close packed, one is simple cubic, one is face-centered cubic, maybe it's amorphous, maybe it's a polycrystal, maybe it's large grain polycrystal, maybe it's a small grain polycrystal, maybe it's a single crystal. Materials have different structures. And then within that, there are also different bond types. Electrons are going to be bound differently depending on the bond type. And so our ionic materials, the electrons, we have electron transfer. For covalent, we had electron sharing. For metallic, we have our sea of electrons. And our van der Waals, we have no electron interaction. Now, we get our dipoles from our electrons, but there's no interaction between neighboring molecules or atoms unless it's just the fact that it induces a dipole on it. But it's not sharing electrons. Electrons aren't moving around in our van der Waals type. And so all these things are very, very important. And so we want to talk about two mechanisms. The first one is called phonons, or sometimes called our lattice vibrations. A phonon is a discrete or quantized unit of vibrational mechanical energy. Basically, it's a mechanical photon. Information, and in this case it's our physical or mechanical information, can only be transferred through a material by phonons, and this happens at the speed of sound. No material is perfectly rigid. If I tap on a material, I displace the surface atoms, which will then bump into the next layer, which then bumps into the next. Each time they bump, they transfer a little bit more energy. So here's my awesome picture of my hammer. And I'm swinging this hammer, and I hit my atom. And when I do that, it knocks this surface atom into the next atom in my material. I have time moving as we go down. And so after a little bit of this energy has been transferred over to this next atom, it's going to transfer energy to the next one after that. And now all these ones are transferring energy. And we can see what that's happening is we kind of have this wave that passes through our material. We call these lattice vibrations, or we call them phonons. But this is how information is passed, mechanical information, things like heat and our kinetic energy. It's by actual interaction between these atoms or molecules. So that's the first one. Phonons. The other mechanism that we can transfer heat is by free electrons. Free electrons are electrons which are not bound, or at least tightly bound. This happens a lot in metals. Metals have loosely bound electrons. Those are the sea of electrons. They're those weakly bound d orbitals. Even though they are technically bound, they're free to move a lot more than in other materials. As electrons gain energy and they move, they're going to transfer some of that energy to other atoms / electrons that they come in contact with. And so this is my picture of my sea of electrons. I have the circle with the plus in it. That is not just my nucleus of my atoms. This is the nucleus plus all of the full shells that my atoms bring to the table. And all of my unmet shells, my d orbitals and such, are the blue electrons. And those are kind of free to move and migrate. That's why they, we'll talk about this in a bit, that's why we get electrical flow so well through our metals, but it's also why we get good heat conduction in our metals, because these electrons can absorb some energy, some heat energy, and they're free to move around and transfer that energy as well. All right, so this kind of jumps into thermal conductivity. It's how heat transfers through something. How easily or how quickly our heat will move through materials. One of the most interesting things that I guess I've found, and it still blows my mind when I think about it, it is how our brain tries to tell us something about heat because of the temperature around us, but really what we're temperature a lot of the times is just our thermal conductivity that we're measuring. An example of this is you're probably sitting in a room somewhere and you probably have some type of material around you that's maybe a little bit more fluffy, it's a little bit more soft, it's maybe made out of a polymer, maybe it's some type of clothing or a rug or something like that. If you touch that, it's going to feel somewhat warm. And you might have something that is a more hard material, something like metal or ceramic. And if you touch that with your other hand, unless there's a reason why it should be warm, like you're using your phone and your phone has been creating heat. But if you touch two things that have kind of been normalized temperature in your room, that soft material, the polymer, the thing that's fibrous, is going to feel warm, and the thing that's metal is going to feel cold. And that's a very interesting thing to me because they're both at the same temperature. I have this thermometer and I can check the temperature of things, and two things can be at the exact same temperature, but yet they don't feel like they're the same temperature. We have this equation for thermal conductivity. Q again is our heat flux. Our K here is our thermal conductivity. And we have this gradient here. Our change in temperature over our K, over our distance, that's our temperature gradient. This should look like Fick's first law of diffusion, and it is very similar to Fick's first law of diffusion, because this is nothing more than heat diffusion. It's how heat diffuses or moves through our material. So what is K? Because that's a big question here. Heat flux, that's how our heat moves, how our temperature changes with distance. I think we can picture that one, but K, our thermal conductivity, what exactly is that? Our K is a sum of our thermal conductivity due to our different types of mechanisms. We have a mechanism for our lattice vibrations, K subscript L, and we have thermal conductivity due to our free electrons, K subscript E. And if I sum those together, I get my total thermal conductivity for my material. If I have something like a metal has a good structure, and it also has lots of free electrons. That means that I'm going to have lattice vibrations plus free electrons. That's going to give me a high thermal conductivity. That's going to mean that there's going to be a lot of heat flux. If I have something like a ceramic, try to figure out what my lattice vibrations should be and what my free electrons should give as far as our thermal conductivity. And what about things that are covalently bound and things maybe that are bound due to van der Waals forces? So think about that. Again, things that we can talk about in our class, how our bonds determine our thermal conductivity along with our structure. So right here, the question is, what types of bonds have which type of conductivity? I do want to show you a short video. I went ahead and I got a sheet pan out, and I put a piece of cardboard on this sheet pan. I left it on my table for 10 or 15 minutes. I wanted both to be at the same temperature. So I took the temperature of both. My sheet pan was at 75.5 degrees Fahrenheit, and my cardboard was at 75.5 degrees Fahrenheit. If I were to have touched both, the sheet pan still would have felt cooler, but they were at the exact same temperature. And so I have this video here, and I'll play it a few times because it is a hyperlapse video, and it happens very, very quickly. All right, so that was quick. Here is the picture one more time. I go ahead and I set my ice cubes down. I take 2 ice cubes. One I set directly on the metal tray. The other one I set on the cardboard. They're both at the same temperature. And as I let this happen, I did this for 3 minutes. This hyperlapse video compressed 1 minute into 1 second. And you can see this is a 3-second video. And so what happens is, over the 3 minutes, we see that this bottom ice cube, the one on the metal, starts melting actually relatively quickly. And remember, the tray is the thing that actually felt cold. The cardboard was the thing that felt warm. But the ice cube that is in contact with the thing that felt cold is actually melting faster. And so when we get to the end here, I move the ice cube out of the way that's on the top so we can see what's happening underneath it. And it hadn't started melting at all. This one on the bottom after 3 minutes is almost completely melted. So I'll play this one more time at full speed. And that is a picture of thermal conductivity. One of them is conducting heat more. It is taking the heat from the ice cube at a faster rate, and that's actually why it feels cold. It feels cold because we feel the stealing or the transferring of that thermal energy at a higher speed than we do with something that is not transferring that energy nearly as quickly. All right, so now what we're going to do is we're going to jump into how heat and bulk materials actually work. So what a casting is when I take and I pour a molten material, let's say a metal, into a mold and I let it solidify, I let it cool. So this is my mold here. I have this U-shaped mold, and if I pour something into it, the first thing that's going to happen is on the surface of this mold, things are going to solidify rather quickly. And so all of these bumps here, each bump would be a different grain. These are very small grains and they freeze relatively quickly. These are called, or this is called my chill zone. That's where it cools quickly and it is small grained. That's actually going to act like a little bit of an insulating layer while the next layer starts to cool off. The temperature cools and I end up kind of getting these columns. The grains are going to be larger, they're going to be column shaped, reaching into the material. And this is called the Columnar Zone. Cools a little bit slower. They're column shaped. They're kind of growing into the material as the material starts to cool because it's cooling at a slower and slower rate. In the middle of my material, I end up getting just large grains. These are cools very slowly compared to the rest of the material, large uniform grains, and we call this the equiax zone. Equiaxed zone. The axes of these are equal in all directions, basically. We have one more thing to talk about here, and it is the picture of what's happening on the surface. When I first pour this in, it's at a nice level. It's nice and full, nice flat surface. But we've talked previously about how materials, especially things like metals, as they cool, they contract, they get smaller. And so the surface is going to actually cool pretty quickly. It's opened up to the air, it's going to cool off. And the middle is going to take longer to cool. And as the middle cools, it's going to contract. And what's going to happen is it's actually going to pull the top down a little bit. It used to be kind of this straight line here, but it pulls it down. We call this our shrinkage. We call it that because the middle of our material has shrunk and it's caused this little indentation in our material. Some materials, when they freeze, they actually expand a little bit. And so I wouldn't get shrinkage. I would get some type of expansion that happens with things that are water-based, like ice cubes. As you freeze them, they're going to expand a little bit because of the structure which they are. But when we cast a lot of things that we cast are metal, and we do get these different zones. We get this chill zone, we get this columnar zone, we get this equiax zone in the middle, and the top has shrunk, and it's actually going to cause some stresses in the material because of this. Now, if I get a piece of material like this, it doesn't necessarily have great properties everywhere, because on the surface I have these small grains, I have these textured grains with these columns, and then in the middle I have these large grains. I have where the shrinkage is at, I have some stresses and stuff that are happening. And so sometimes what we want to do is we want to be able to alter the physical and chemical properties of the material. And we're going to do that with heat treating. Before we talk too much about different types of heat treating, I want to talk about what recrystallization is. Recrystallization is when the grains in a material nucleate and grow, removing stresses and many defects. These grains will grow and then consume old grains. So over here on the left, I have this picture of some grains, and this material has some stresses in it. It has some defects. I just put some dots and some slashes and some dislocations and stuff in here, just showing you that there are some problems inside this material. Maybe this material has been worked and it's been bent, and it has just some stuff that we've done to this material. And what I want to do is I want to try to fix it. I want to take those things out. what I do is I begin by heating it. I start heating my material. And every place, or a lot of places I should say, that there were some stresses, there were some defects, it's going to start growing a new grain. So even within a grain, it can start growing a new grain because it's trying to recrystallize, it's trying to fix those defects. So when we first start recrystallizing things, we get very, very small grains that start growing, and they start growing all over the place. I'm not going to continue drawing this out, but the picture is I get these small grains everywhere. As I continue heating it, some of these grains are going to expand, kind of consuming. It's going to start taking up some of the nearby grains or old grains. And so the longer I heat it, these grains will continue to grow until they get to a certain size. And so that's what recrystallization is. So now let's talk about a couple types of heat treatments. One is annealing. If I anneal a material, I heat it above the recrystallization temperature, the temperature that allows this process above to happen. And then I let it cool in the furnace. I don't take it out. It would just be like if I cook something in the oven, and instead of taking it out when it's done, I just turn the oven off and I let it sit in that hot oven for a while. This allows grains to grow. It improves ductility and toughness. Ductility we'll talk about, and toughness we'll talk about more when we get to mechanical properties. But in short, ductility is the opposite of being brittle, and toughness means that it can absorb a lot of energy. In this case, our solid phases can change during cooling. So if we look at our phase diagrams, I'm letting it cool very, very slowly. I'm allowing these phase changes to happen even within my solid structure and material. And I'm doing that because I'm not removing this heat very quickly. I'm allowing it to cool very, very slowly so phase changes can happen. Normalization. It's when you heat above a recrystallization temperature and then you pull it out of the oven when you're done and you let it cool in the open air. So it's very similar to annealing, except for you just let it cool in the air when you're done. In this case, the grains do grow. It will improve ductility and toughness, but because it cools a little bit faster, it often retains some strength and hardness. And again, because it's not cooling off super, super fast, solid phase changes can occur during cooling here as well. Quenching. We heat above the recrystallization temperature again. But when we're done, what we do is we cool it very quickly, and we can cool it in lots of things, but we're going to cool it in a dense fluid, not air, but we're going to do it in some type of liquid, something like water, oil, or polymer, something like that. It's going to cool it very, very quickly. What it's done is it's allowed us to start growing grains. So we kind of get into this middle picture here, where we're starting to grow these grains. We have lots and lots of little grains. But then what we do is we freeze it, and we don't allow these grains to continue growing. What this does is it improves our strength and it improves our hardness. It freezes the microstructure. There's little change in phases while it cools here. It doesn't give it a lot of time for phases to change. And it causes small grains to have happen. Lastly, the one we're going to talk about is tempering. If I temper something, I'm going to heat it below the recrystallization temperature. All the ones above here, we heat above the recrystallization temperature. We often temper something after we quench it. What we do is we heat it, but we heat it at a lower temperature. And what it does is it just removes some of those internal stresses, so we can use it to balance and tune the physical properties. If I freeze things too quickly, it can cause internal stresses. And so I just want to relax a few of those from the very, very quick cooling that we did. And so a lot of times we do temper a material after we quench it. All right, so I want to mention one more thing. We're going to talk about glass, and this is, again, window glass. It's not the amorphous type of glass, but if I have something like window glass, silicon dioxide, theoretically, glass is a very, very strong material, but we all know that glass is brittle and it breaks somewhat easily. At least some glass does. The reason for this is because there are imperfections on the surface that weaken the material. I've definitely exaggerated these weaknesses in the pictures below. But if I want to strengthen this material, one way I can strengthen this material is if I have these little surface cracks, these little surface imperfections, what I can do is I can heat this and I can let the outside cool and let the inside cool more slowly. What that does is it allows the center to be kind of expand because it's hot. The outside, the top here is going to freeze in place while the inside is still expanded and hot. If the inside is expanded and hot, we're actually going to get, and the top freezes, what's going to happen when the middle starts cooling off is it's going to shrink. That same idea of shrinkage, and as it shrinks, it's going to start pulling the top down, the surface down a little bit, and it's actually going to close up some of these cracks. And so when we have tempered glass, what we've done is the surface imperfections are still there, but we've added a bunch of stresses inside the material that are helping pull those imperfections shut, so that the material is a little bit stronger. But that's only up to a point. Anybody who's ever seen tempered glass breaks, when it does fail, it fails catastrophically. The whole thing just breaks apart. And the reason for that is because all of those stresses that were holding this material together, when one fails, it's like a domino effect, and all of those stresses let go all at once, and the whole material falls apart. Another thing you can do with glass is you could diffuse larger atoms into the surface. These larger atoms will cause surface compression. So let's say that I have this material, and on the surface, all of my atoms are about the same size. But what I'm going to do is I'm going to diffuse something into here where some of my surface atoms are going to be larger. These larger atoms are going to push these cracks on the surface. They're going to push them shut. Again, what it's going to do is it's going to cause internal stresses, and those internal stresses are going to make the material act differently. An example of this would be Pyrex. It's a glass that is very good for high temperatures, for baking, for heating and cooling. And the reason that it does that is because we have added things in which are going to press those surface imperfections. They're going to keep those surface imperfections from breaking a little bit more. And we have a new product, a product that we can work with. I'm not going to watch this video with you. You guys can go ahead and watch it. I'm not even going to add the link to it. You can do a search for it. It's on YouTube. Smarter Every Day has a video called Mystery of the Prince Rupert's Drop at 130,000 frames per second. They do this in slow motion. They talk about some of these things about glass and about shrinkage and a bunch of the topics that we talked about. They make pretty good videos. I would recommend, if you have time, going ahead and watching that, and we can discuss that more in class as well.